Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aisyah bint Abdul Ghani. Today we want to present about operational amplifier using LT Spice. We have 5 amplifier configuration. First is inverting amplifier. Second, non-inverting amplifier. Integrator, differentiator, and summing amplifier. The objective of this lab is to understand the basic characteristic of common op-amp configuration. Second, to analyze 5 circuits, which is inverting, non-inverting, integrator, differentiator, and summing amplifier. Next, to compare theoretical calculation with simulation result using LT Spice. To observe how resistor, capacitors, and op-amp offset voltage affect output signals. And the last one is to understand the behavior of op-amps in analog signal processing application. The first one is inverting amplifier. How the circuit produce an output that is inverted and scaled by the ratio of resistor. Second is non-inverting amplifier. Observe how the circuit amplifies the input signal while maintaining the same phase. For summing amplifier, investigated how multiple input signals are added together to produce a single combined output.
Okay, for the integrator, we analyze how the op-amp performs mathematical integration, converting square wave into triangular waveform. And for differentiator, we study how the circuit differentiate the input signal, producing sharp output change based on input slope.
Next, we move the simulation and circuit demonstration. The first one is inverting amplifier. The input signal is applied to the op-amp's inverting negative terminal from a resistor R1. The output signal is feedback to the inverting input through a feedback resistor, which is from RF or R2. The function is it amplifies the input signal and inverts in phase a 180 degree phase shift. The output signal will look like an amplified mirror image of the input signal. For the second one is non-inverting amplifier. The input signal is applied directly to the op-amp's non-inverting, which is positive terminal. A voltage divider made of R2 and R1 is connected to the inverting negative terminal. The output signal is feedback to the inverting input through the feedback network. The function is the amplifies the input signal without changing its phase, a 0 degrees phase shift. The output signal is an amplified version of the input signal.
Hi, I'm Nur Fadli Nazlifa binti Muhammad Sokri, and I would like to talk about the integrator circuit. The component that primarily makes this circuit an integrator is the feedback capacitor, which is C1. In this inverting op-amp configuration, the capacitor is placed in the feedback path between the output and the inverting input. A capacitor's voltage across it is proportional to the integral of the current flowing through it over time. Since the input current flows almost entirely into the feedback path, the output voltage must change over time to keep the inverting input at virtual ground. This change is precisely the integration of the input signal. Then we have input resistor, which is RS. While C1 performs the integration, RS is essential for the circuit operation. It converts the input voltage into a proportional input current that flows into the capacitor. The RS-C1 product determine the time constant and the scaling factor of the integration. Let's move to the comparison of expected versus observed result in integrator op-amp circuit. The expected output was a smooth, linearly increasing or decreasing waveform, which is ideal integration of the input. The observed output followed the integration trend but showed slight drift and small distortion compared to the ideal theoretical waveform. Then, the different input offset voltage caused the output to drift over time, especially because the integrator has high gain at low frequency. Bias current charging the capacitor introduced additional unwanted slope in the output. The finite gain and bandwidth of the real op-amp caused deviation from perfect integration at higher frequency. Then, the required feedback resistor, 10 mega ohm, helped reduce drift but also made the circuit more sensitive to noise. Adding the 10 mega ohm resistor improved long-term stability but reduced ideal integration behavior. Using a larger capacitor helped reduce noise but slow the circuit response. The op-amp supply voltage limits the maximum swing of the integrator output, preventing perfect integration of large input amplitude. Next, high sensitivity to small DC offset means integrated circuit require careful design to avoid output saturation. Okay, next we move to the next circuit, which is differentiator circuit. The component that makes a circuit a differentiator is the capacitor when it is placed in the input path in series with the input signal and the resistor is placed in the feedback path. Okay, for the input capacitor, which is CS, it is connected directly between the input voltage source and the inverting input terminal of the op-amp. A capacitor current is proportional to the rate of change of voltage across it, because the inverting input is a virtual ground, which is 0 volt. The voltage across the capacitor is essentially Vin. Next, we have RF, which is feedback resistor. It is connected in the feedback path between the op-amp inverting input terminal and its output terminal. This resistor converts the current flowing through the capacitor into an output voltage. For the differentiator circuit, the comparison of expected and observed result is the expected output was a waveform proportional to the derivative of the input signal. Example, a square wave for a triangular input. Then, the observed output reflects the derivative but contain high frequency noise and slight waveform distortion compared to the ideal case. High frequency noise was amplified because the differentiator inherently boosts higher frequencies. Finite op-amp bandwidth and slew rate limited the accuracy of the derivative at rapid input transition. Input bias current and parasitic capacitance affected the output slightly, causing small deviation from ideal behavior. Adding a 100 picofarad capacitor in parallel with the feedback or input helped filter noise and shape waveform. The small capacitor improved noise filtering but slightly reduced differentiation accuracy at very high frequencies. High gain at high frequency make the circuit sensitive to unwanted signal and noise. The op-amp supply voltage limits prevent the output from reaching very high amplitude, causing clipping if the input changes too quickly. Careful component selection is required to balance responsiveness and noise suppression.
Next, we move to summing amplifier. We use two op-amp, and it is designed to add multiple input voltage together. The input voltage is labeled V1 and V2 are applied through separate resistor, which is R1 and R2. The circuit has a feedback resistor, which is RF, is connected between the output and the inverting input. Because the inputs are connected to the inverting terminal, the output voltage is the sum of the inputs but with the opposite sign. The waveform displayed below, the circuit shows the input signals in green and the resulting output signal blue of the summing operation.
Next, we're going to talk about discussion for this lab. The op-amp circuit generally behave according to theory, with some differences due to practical limitation. Also, the output clipping occur when the inverting amplifier exceeds the supply voltage limits. Next, component values significantly affected performance. Large resistor in the integrator help prevent output drift, and small capacitor in the differentiator reduce high frequency noise. And lastly, the difference between theoretical and measured results were influenced by component tolerance and op-amp constraints.
And the last is conclusion. The experiment confirmed how different op-amp circuits behave, show differences between theory and real calculation due to practical limits, and demonstrated how key components like resistor and capacitor affect circuit stability and accuracy.